Hello friends, we are going to discuss today about one more type of welding as you see here in this chart or the slide. It's a fillet weld. As the description given here you see, the fillet weld joints are not only the most frequently used weld joints but also one of the most difficult to weld with any real degree of consistency. So we are going to discuss uh, as a primary observation, fillet looks to be simple to weld as you see the entire fillet welding yourself, unlike the butt joint where we are going to hide most of our runs in the subsequent layers and there is no visibility as to what is happening inside the groove. But any type of a fillet joint as you see here, whether it is a corner joint, single side, double side, or we have these are kind of a lap joints, these are corner joints, but this is a classical fillet which is shown here with its root, throat, which is explained better here in this real photograph of the fillet, that you have a vertical member and horizontal member put at normally at right angles, but sometimes it may be at some included angles in case of a structural welding like TKY joints, where there would be a small angle going from 30 degrees to 45 degrees and the fillet is after the butt joint. But most important part what we need to understand, unlike a butt joint which has a full penetration, fillet through this vertical face of this vertical member, the horizontal face of the vertical member, we are not going to fuse it all through unless we give a groove and a fillet. So groove and fillet joints are also used quite often where this kind of a stress risers or a notch is not acceptable, and critical equipments like in nuclear and other industries will have many times even this vertical member which has a slight groove or a Z both sides or single side, and then it is welded first and then on top of it we build the fillet. But if we consider only fillet weld, which is most of the times we use it in our pressure vessels, we have to look into two important parameters. The fillet design, unlike in the butt joint where we very rarely weld partial butt joint. Always whatever is the thickness, that's completely filled up with proper root penetration and reinforcement on the top. But in case of fillet, depending upon the stresses which are going to come, which we'll see in the subsequent slides, we will choose the throat. Even though the leg of the fillet is easy to measure, this is the leg of the fillet as you see here, the L and L. But what is important, where the actual load factor of the fillet is going to be taken, is this the cross section of this weld. So this is called as a throat, the theoretical throat and the actual effective throat, because of the penetration or reinforcement or concavity. The resultant of that will give the actual throat, and that's what is going to carry the load and the stresses between this vertical member and the horizontal member. So what we are going to do is we are going to see how to deposit this weld in a proper manner and how do we ensure that we achieve this throat and at the same time there are no defects. So like any other our weld principle, if you cut right, you set right, if you set right, you weld right. That applies even the fillet also, that if we are able to really put this vertical member on horizontal member with as close gap as possible, that means this edge preparation has to be cut correctly. This plate shall be as flat as possible, the horizontal plate, and we should try to fix it with the 90 degrees on both sides, that is right angle, and tack it and ensure that it doesn't bend. Otherwise we'll see in the subsequent slides that how if the plate gets inclined, or for lap kind of a joint, if this plate which is on the top gets lifted up by some distance either at the joint or at the other side, it is going to create a improper joint there, and then welder will find it difficult to weld. Now, why we are saying this is a little difficult to weld as compared to a butt joint is, in a butt joint both sides are normally kept same, unless it is a single V and we have only one side, then it becomes difficult to weld. But in fillet, even though we have full accessibility, the placement of weld bead to achieve correctly legs and the fillet or the throat is the most important criteria, and this placement has to be done in two directions, which we are going to see it in the next slide. So I will move to the next slide now. Now, as we were discussing, say one of the angle where in the direction in which we are welding this, so that angle of the electrode is required to be maintained as suggested here, 60 to 70 degrees. For most of the processes, we maintain this 60 to 70 degrees in the direction from where we are going to continue. But in the other direction, the cross section of it, we have to be as perfect as possible depending upon the position where we are putting it the fillet. So as you see here, for the first layer we are starting with 45 degrees, but as we go to the second layer, we don't want it to spread onto the horizontal plate. It should be on more onto the earlier fillet, so we increase this angle from 45 degrees to 70 degrees. And similarly, if we are going for the next one, I know that this video we are getting our thing, but I will try to move it when the movie will be made. And here if you see, this angle is exactly reverse. We go from 45 degrees to 30 degrees so that we place maximum welding on the vertical plate, and by gravity it is going to fall down. Here by gravity it is going to fall down, we are deliberately putting it onto the earlier fillet, so angle is 70 degrees. So this maneuvering of the torch angle, weld angle, or even our submerged arc welding when we are going to place our torch or the nozzle, and on the other direction it has to be 60 to 70 degrees. So this is one difficulty what we face, and as you see here in different passes, it has to be maintained. The fillet may not be achieved in one single run. There are few methods which is not very widely used, where in single run we try to cover by little weaving, which I will show it in the next slide, for nozzles. But most of the time we will build it by placing number of runs. So first we'll create a fillet. Suppose the fillet is of 20, first we'll create a fillet of 8, then 12, then 16, and then 20. So the number of runs which are going to increase from 8 to 12 to 16 and 20 are quite large, quite big in number. Here it is only one fillet which you are seeing it. As you see here in this photograph, see the number of fillets how they have done it, and so nicely they have done. So what is important for us, which we'll be saying it in our third slide, is where the concentration, the stress concentration is going to happen, and where after welding there will be a internal stress which is going to get developed because of the shrinkage. Like a butt joint, there is a shrinkage. Here also there is a shrinkage, and it is said that if you take two plates right angle to each other and try to put a tag there, the amount of force by one single tack of 3 millimeter length by 3 millimeter fillet can take few hundreds of tons of load, or can create a shrinkage force. And that's where a very thick plate also you will see, starting from the fillet, it bends. It either goes this way or this way depending upon where you are going to do a fillet. And that's because, once again, like in the butt joint, here we have the least of the weld, and here we have the very large width of the weld which is going to shrink. So the shrinkage here is less, shrinkage here is more, and natural tendency for this, the vertical member, is to bend down towards the horizontal member because of this larger width of the weld which is going to shrink. Now, to avoid that, we have to ensure that nowhere in the corners we will have a stop and end point. As it is, the corner joints are already highly stressed, and the last weld which will be doing it here, which you'll see it in the subsequent slide, is also a highly stressed one, because already there is so much of weld which has happened before we deposit the last layer here, and we will start building up from the bottom. So the last layer is always going to be from top to bottom. Now while doing that, like in the butt joint, we also have to check and ensure the setup. So a good setup can give a possibility of very good weld. A bad setup can create a problem for us. We will not be able to measure the throat correctly, we will not be able to weld it correctly, there will be a air gap which is going to be remaining here. And if it is a fillet with a lap kind of a joint, there is a possibility of the corner, because of the arc voltage, getting melted down. And if we are not going to give the fillet, we have to be very careful in directing, and we may go from 45 degrees to 70 degrees to avoid this corner joint or corner melting. Otherwise it will be a defect. And if we do too much of vertical 70 degrees, there is a chance that we may have a lack of fusion on the horizontal plate or the second plate, and that may create a problem in the weld. It will be a defect. So while welding a fillet, so many areas, so many angles are required, unlike in butt joint where we have only one direction to really monitor and see that we have sufficient gap for depositing. Here there is no question of gap, because everything is open. We have to ensure that what we deposit is the right way, and if we make a mistake, not only the fillet leg or the throat will not achieve, but there could be a excess deposition on one side to achieve the throat, or there could be a concavity, or there is a convexity. Both are not good. If it is too concave like in this photograph, or too convex like in this photograph, the toes or the throat is going to suffer. The toes are very susceptible for high stress in this kind of a convex joints. And in concave joints, even though we measure the leg lengths to the requirements, but the fillet is going to be lesser to the extent of this depth of depression. So lot of things welder has to really do it and position it, and that's where I decided to make this 3 separate slides on the fillet, irrespective of the material. If the material is sluggish, and if the material is not going to flow, and if there are nozzles where the accessibility is an issue, then still further our welding is going to become a challenge. And that's where don't take fillet welds very easy. They are also equally important for us, and a small defect or improper welding can create a failure. As we will see in the next slide, the stress concentrations are going to be much higher. Now we are on the last slide of the fillet. As you see, there are 2 types of nozzles, set in nozzle or set on nozzle, and both have a groove to be filled up and fillet to be given on top of it. So a typical nozzle, welded nozzle, will look like this. There is a flange which is normally set up to the pipe before we put it onto the shell. And similarly, if there is any secondary nozzle, that also is welded before we keep it. And both this flange and the secondary nozzle is the one which is going to create a hindrance, accessibility for the welder. And then the shell radius, as you see here in this photograph, in the one side, this side of the weld, you will see a good joint which is coming up here, but on the other side, this angle is going to become quite large. This angle is going to become less. This angle is going to become quite large. Similarly, in this the TKY joints, which I gave example earlier, in the structural welding, where it is not at right angles, but it can be between 30 to 45 degrees or even 60 degrees. And then the accessibility in this corner here is very difficult, whereas almost out of 360 degrees, 20 to 30 degrees is only the most critical portion in this joint, which is very carefully required to be welded, whether it is a butt or a fillet. But on the other side, it becomes much easy. But this is the joint which is required to be taken care. As you see here, the number of passes which you are going to do it, and the placement of each of this pass becomes very critical. So coming back to our nozzle welder, what we do is the number of the weld lines or the number of passes in this area may be lower than the number of passes which are required to be built here, because our fillet is going to be measured from this height as you see here, where we have to get the throat here, whereas here achieving a throat in this direction of the weld is easy, in this direction it becomes little difficult. So number of passes are going to vary. So how to start and stop this number of passes and where to merge as you take 360 rotation on the weld becomes important. And finally, the stress values, if you see here in this particular thing, see what is the measurement near to the toe of this upper fillet, which is the last one to be welded, has gone up almost 33% higher, 30 to 33% higher, from 3000 water units to 4000. So there is a jump of almost 1000 units in the stress level, and that's how it comes into raid. So this is a portion, and both sides we are going to weld it, so it is not only this side of the weld is highly stressed, the other side of this plate is also highly stressed because there is a fillet on the other side. And if there are any defects which will land up into this because of the gravity, weld is going to fall down, and there are undercuts or there are improper fusions, the reinforcements are not good, then we will have the worsening of this already high stress level with the bad impact of the weld profile. So I will say that even though fillet looks to be easy for qualification in PQR or WPQ, but executing it onto the actual job with this reinforcement pads or without reinforcement pads is difficult. And that's where, to avoid that, sometimes this kind of a weaving with a very large nozzle to shield it is practiced, but more or less this is not acceptable by many codes because of the so much of weaving which is being done. And after weaving also, you are not sure whether you are going to get the sufficient the reinforcement on the fillet, otherwise there will be a recess as we saw it in the earlier slide, and that may not qualify for the required throat length. So positioning of these weld beads, getting this throat, ensuring that there are no defects, undercuts, no stress points, fusion between the layers, fusion with vertical wall, fusion with horizontal wall, all are required to be seen, taken care. And if it is a nozzle, and especially a nozzle which is at angle, it becomes still more difficult, and lot of practice, care has to be taken. I am sure with these inputs you will be able to really look the fillets into a different way, which is normally considered as very easy, is no more easy. Placement of fillets is very critical. The start of fillet is also very critical. Where are you actually tacking it so that you have the best point where it gets locked? Like in our earlier slide, if you are tacking it on the sides, if it is possible to do it, most of the time it is not there. So are we going to tack it on both sides? Alternatively, are we going to give some gussets to hold the plate in vertical direction, not allow when we are going to weld, we are going to check every time. In case we see that it is bending towards one side, immediately we should stop on this side where we are welding and go on to the other side and start welding from that side, and make it within the welding stresses itself. You try to manage to keep it vertical, or best is to really have both the welders simultaneously welding from each side so that the stress levels are balanced and the job doesn't distort or the vertical member doesn't bend from 90 degrees to either this side or that side. And then physically we will have to correct it. If you try to correct that physically without the welding, this highly stressed point which is seen here, the red line on the top of the fillet, is the one which is likely to crack. That is where the crack will initiate, and the weld will remain intact, but the parent metal will crack, and then we'll start blaming parent metal, or there may be an inherent defect. My welding is good. That may be a possibility. I'm not saying that the parent metal may not be bad, but since we know that there is going to be a stress concentration and the placement and the distortion, it is welder's duty to really see that while he is welding, it doesn't distort, it doesn't give more stresses onto the top of this weld. So this weld, the last weld, is the most critical weld which has to be deposited as shown here, and we have to take utmost care in this last run so that we don't land up into any defect, porosity, cracks, or the undercuts or linear indications in any of our DP or X-ray. Ultrasound and X-ray in fillet is not easy like butt joint. Very uh, carefully we have to do this test. A qualified person who has experience can only interpret it very well. Otherwise, as we saw in the earlier case, the root gap which is seen here, that may reflect as an indication for the fillet defect. So calculating where exactly are we going to this unfused area, which is not possible to fuse unless we give butt joint here, like in this nozzle sort we do it. Normal fillets we just keep it on top of it and weld only edge to edge and not penetrate into the thickness side. So these are all the considerations which are required to be brought in, and once we do that, I think our fillets will be good. Lot of care is required to be taken in structures, in our pressure vessels, and especially when the equipments are for the critical applications. So that's why these three slides, in my opinion, are the most important for any welding engineer to concentrate. Enjoy welding, do it good, do it well. All the best. Thank you.